temperature, and rate. As the temperature of a reaction increases, the rate almost always increases as well. Why is this so? If we think about the rate expression, changing the temperature does not change the concentration of the reactants, at least not significantly. So if the rate changes, then the change must be due to a change in the only other factor in the equation, the rate constant K. The question arises then about why K changes with temperature. What is K measuring that is affected by the temperature? The theoretical basis for understanding this effect is called collision theory, or the collision model. It has three basic points. Point number 1 says this: in order for a reaction to occur, molecules must collide with each other. Without a very near approach of the reacting molecules, the breaking of bonds and the formation of new ones, the definition of a reaction, cannot occur. The changing of the bonds is a rearrangement of the electrons, and this will not happen without the molecules being very close together. However, not every collision produces a reaction. The collision must have enough energy to be able to break the bonds that will be broken. So point number 2 is, only those collisions that have sufficient energy can react. It takes energy to break bonds, so the collision has to have enough kinetic energy to be able to break the bond. In addition, if the molecules collide with the wrong orientation, so the wrong atoms are near each other, the reaction will not occur. Point number 3 says, the collision must also have the molecules oriented in such a way that the rearrangement of the electrons can happen easily. The minimum energy needed to allow the reaction to occur is called the activation energy. Just as a ball cannot get over a hill if it does not roll up the hill with enough energy, the molecules cannot react unless the collision has enough energy to overcome the activation energy barrier. Anything that affects the rate of a reaction must have an impact on one or more of the following 4 things. 1. The number of collisions that occur in a given time. 2. The energy of those collisions. 3. The energy needed for the reaction, that is, the activation energy. Or 4. The orientation of the collisions. Temperature affects the energy of the collisions and the number of collisions. In order to better show the transition from reactants to products, we draw a reaction energy diagram. The diagram plots the potential energy of the molecules as a function of something called the reaction coordinate. The reaction coordinate is not related to time, but is rather related to how far along the reaction is in going from reactants to products. This particular diagram is for the rearrangement of methyl isonitrile into acetonitrile. We begin on the left with the reactants at the beginning of the collision. As the collision occurs, the kinetic energy of the molecules is converted into potential energy, and the potential energy of the system rises as the bonds in the reactants break and the bonding begins to rearrange. Eventually, when the collision has produced an amount of potential energy equal to the activation energy, we have reached a transition state. In the transition state, the molecules in the reactants form what is called the activated complex. In the activated complex, the reacting molecules are midway between the reactants and the products. The atoms are between where they were in the reactant molecules and where they will be in the product molecules. And the bonding is also in between what it was in the reactant molecules and what it will be in the product molecules. Once we have reached the activated complex, the reaction can continue to the products. As the new bonds continue to form, they release energy. This continues until we reach the end of the diagram where the products are. In the diagram, we have the energy of the reactants and the energy of the products. Therefore, we can identify the change in energy of the system, delta E or delta H. On these diagrams, we have two significant energy relationships, delta E or delta H, the difference in energy between the reactants and products, and the activation energy, which is the difference between the reactants and the transition state. On this particular diagram, we have the models of the molecules drawn out, so we can see what is happening to the bonding and the molecular positions as the reaction progresses. This is not usually done on these diagrams, but it can be very helpful. The successive positions have been numbered 1 through 5, so you can see the progress. Maxwell-Boltzmann distributions. Temperature is a measure of the average molecular kinetic energy of a set of molecules. So changing the temperature clearly is going to affect the kinetic energies of the molecules and will impact the rate of the reaction. At any particular temperature, there is a wide range of molecular speeds and molecular kinetic energies. The distribution of the energies is called the Maxwell-Boltzmann distribution. As the temperature increases, this distribution widens and flattens out, meaning that there are more molecules with higher energies and fewer with lower energies. A similar distribution can be drawn for the collisions, with a similar change for collision energy as the temperature rises. The dotted line in the diagram represents the activation energy. Only the molecular collisions with at least the activation energy can react, usually a tiny fraction of the collisions. As the temperature increases, a greater fraction of the collisions have the activation energy, so the rate of the reaction increases. The fraction of molecules with enough energy to react can be found through this expression, where E sub A is the activation energy in joules per mole, R is the gas constant in joules per mole Kelvin, and T is the Kelvin temperature. A Scandinavian chemist, Svante Arrhenius, adapted this equation to relate the rate constant K to the activation energy. The equation is K equals A times e to the power minus E sub A over RT, where A is the frequency factor, a number that represents the proportion of collisions with the proper orientation for the reaction. If we take the natural log of both sides of the Arrhenius equation, we get the equation natural log of K equals minus E sub A over R times 1 over T plus natural log of A. This equation has the general form of a linear equation, y equals mx plus b, where y is the natural log of the rate constant K, the slope is minus E sub A over R, both of these are constant for a particular reaction, x is 1 over the Kelvin temperature, and the intercept is the natural log of the frequency factor A. So, if we determine the value of the rate constant at several temperatures, we can determine the value of the activation energy by graphing the natural log of K versus 1 over the Kelvin temperature and using the slope. Another form of the Arrhenius equation is this form, which is produced by subtracting the equation at one temperature from the equation at another temperature. Note that the frequency factor is gone from this form. In this equation, K1 and K2 are the rate constants at Kelvin temperatures T1 and T2. E sub A is the activation energy in joules per mole, and R is the gas constant, 8.3145 joules per mole Kelvin. There is one problem on graphing and using the Arrhenius equation on the problem sheet for this lesson.